All right, back at it. Lesson 2 of the day. You know the routine, right? Whenever you learn a derivative, you also are learning an antiderivative. So we just learned inverse trig derivs. Hey, now we're doing inverse trig antiderivs. Okay, good stuff. So here we go, crew. So in the previous lesson, this is what we learned initially, right? The very first thing we did with the derivs is we found, I worked through the process of finding the derivative of inverse sine x and showed you that the derivative was this over here. Well, if that's the case, right, then if we're looking for the antiderivative of 1 over square root of 1 minus x squared, that means we're trying to come up with a function that if we were to take the derivative of it would become, this right here, right? Would become this. So, obviously that means that the antiderivative of this would just be inverse sine x. Okay, so there you go. All right, so boop, there you go. Now, that is very limiting in that form. So someone was able to come up with a little bit better version of this, and not saying that this is definitely true. I mean, this is a true statement. But someone came up with a little better version of this to be more useful in more forms, and you'll see that right here. So these are the two antiderivative formulas that we need. You'll notice there's only one for inverse sine and inverse tangent. That's it. That's all we're, all we're going to be dealing with. Not going to have 4 different formulas going here. Okay. So you can probably just, anything that's in that form, inverse cosine, you can just kind of get it manipulated into this form here, I guess. So it, between the two of these, it's pretty easy to recognize that if something has the square root in it, it's going to be inverse sine. If something doesn't have the square root, it's inverse tangent. So between the two of those, it's easy to recognize which one you'd want to use. But sometimes it gets difficult, right? So as you're on a test or the final or the AP test, and you have all the techniques of integration we've learned so far, you have the ln rule, u sub, and so forth and so on, the trouble becomes recognizing that you want to use the inverse trig stuff. So let's look here, for example, at this right here, okay? And I'll show you then how this formula works, okay? So each of these formulas definitely need to be committed to memory. Again, obviously for our tests and quizzes, when we're doing distance learning, it is open book, open note. But, if we do AP tests, I'm guessing this won't be open book, open note. So anyways, you can see here that this guy right here, which again also could be written, by the way, as 1 over square root of 4 minus x squared dx. I a lot of times just prefer it in that form. That just looks nicer to me. So if you look at that, again, the first thing when you come to a problem like this is to recognize, hey, I should use this inverse, sine formula, okay? So some people might initially think, hey, let's try u sub. But the problem is if you let u equal 4 minus x squared, the derivative of that would be negative 2x, and there's no x on top that would get canceled out. So u sub wouldn't work in this case, okay? Neither would any other technique. So really we have to use this inverse sine one, okay? So the first order of business is to identify the a and the u, okay? So the 4 right here is in the spot where a squared is. So that means that a is equal to 2, since 2 squared would be 4, right? If I put 2 in for a right here, if I put 2 in and squared, it would become 4. And then where the for u squared, that the x squared is in the spot where u squared is, so that means that u is equal to x. Because again, if I put x in for u right here, I'd put it in just for the u, and then I would get x squared, which is exactly what it's in the formula there. Okay, cool. Now, the one really important thing that I have to kind of make sure and consider is this du on top right here, which is the derivative of u. So I'm going to find the derivative of u, which the derivative of u, x being u in this case, the derivative of x is just 1, okay, dx. All right. So in order for this to work, that 1 has to be up on top, which, hey, look, it is. It's right there. There's the 1, okay? So this is set up perfectly for us. It does not require any manipulation, okay? And so I'm going to go ahead here and I'm going to just kind of plug everything into the appropriate spots now. So inverse sine of u, you can see there is x, okay? Again, that's my x, that's u. So that on the top right here, I put an x. And then on the bottom is a is 2. That goes right there. Put that there. Bam, done, okay? So again, I know I didn't mention it too much at the beginning, but these formulas right here, I know look a little different than the derivative formulas, but I will tell you this, and you can try and work it out. And if you know, but I will tell you that if you do take the deriv of this right here, the right side, and you simplify it, it does require a bit of simplifying. The derivative ends up being this over here. Same thing here. If you take the deriv of that inverse tan and simplify it fully, it does become that over there. So it does work out in this case, and having the formulas like this as opposed to the previous slide make it useful in a lot more circumstances, like this right here. You know, that 4 being in front would, you know, the previous slide was just 1 over square root of 1 minus x squared. That 4 wouldn't have been able to, it would have screwed things up in that formula. But now, okay, I can use that. But again, it's just a matter of memorizing the formulas and then knowing how to use them. All right. All right, let's look at a couple other ones here. So let's, I'll kind of, you know, there's times I'm going to ask you to pause, okay? And then I'll say, okay, and then we'll meet back up. So the first thing I want you to do is to recognize here, okay, obviously between the two of these, we should be able to tell that it's this inverse, that it's the, that it's this inverse tan right here because there is no square root there, okay? And then again, you might be thinking, gosh, is there any other formulas that I could use for this? Could I use ln rule? Well, the problem is, right, u prime over u, if you took the derivative of the bottom is 18x. There's no x on top. You can't manipulate an x. You can't you can only manipulate constants. So, you know, and I'm just going to write this again. It's 1 over 2 plus 9x squared dx. That's the same thing. Just want to make sure it's clear. So here's what I want you to do first. The first thing I want you to do is to try and identify what is your a and what is your u. Okay? What is your a and what is your u? Pause. Find those and then unpause and we'll go from there. So again, I'm looking at A is the constant term, okay? So I match up, that's this term right here, which is the 2. Now the thing is, right, in the spot up here, it's A squared. So over here, 2 is equal to A squared, the 2 in that spot. So that means that A would be equal to square root of 2. So if I put square root of 2 in for A up here, squared would just become 2. U is, you know, this guy here, u squared is there. So the spot, the thing that's in the spot where u squared is 9x squared. So, I mean, you could even, if you wanted to, think, okay, well, I know u squared is equal to 9x squared. If you want to write it out, you can. And then if you were to take the square root of both sides, you would get u is equal to 3x, okay? That could be done in your head as well, just getting that u is 3x, that's fine, okay? Now, I do want to make note of this. You know, the form up here, oops, this guy, the inverse sine one, since it's you know, subtracting, it has to be in that order. But the inverse tangent one, since it's adding, it could switch the order. So I could have given you the problem like this: 1 over 9x squared plus 2 dx, like that. Okay, which is the same thing. I just wrote the denominator in a different order, right? They just switched up the addition order. But it's the same thing. But still, this term would still be your u squared, and this term would still be your a squared. A is always the constant. U is always the variable. Okay, so just keep that in mind, all right? Okay, so now I have to remember, make sure that on top here is du, okay? So at this point now, we've found our a and we found our u, okay? So hopefully you matched up with that and you've unpaused and you've checked now with me, okay? Work along with me right now, okay? And then on the next one, I'll have you guys try it. So I need to find, what is du? So du is equal to, the derivative of 3x is 3. dx. So when I look on top here, aha, not quite what I need, right? I need the top to be 3. Right now, the top is just 1. So it's not right in the form for me to do this. Well, the thing is, it's only off by a constant, though, right? It's only off, you know, I needed the top to be 3, and it's 1. So I'm going to use the same manipulation that we did like when we did the ln stuff, and I'm just going to multiply by 3 over 3. And what I'll do is I'll bring the top 3 inside and leave the bottom 3 out. So it'll become 1/3 integral of, and again, I brought the top 3 inside, 3 over 2 plus 9x squared dx. Now it's set up perfectly because I'd found my a and my u, and now the du has to be 3, and the du is 3 on top. Perfect. So everything is set up just how I need it to be to use my formula here, okay? So now I just go ahead and I, you know, plug everything in. Now I have to remember, I have the 1/3 out in front of the integral. So that has to go along for the ride. So I have the 1/3 out in front. And now we'll start using this, you know, formula right here. So 1 over a. So a, remember, is square root of 2. So it becomes 1 over square root of 2. Inverse tangent of, and then u over a. So u, remember, is 3x. So it becomes 3x over a, we said, is square root of 2. And then plus c. Okay, I'll just close the parentheses there and put my plus c. So I could leave it like that if I wanted to. Of course, I can just multiply the 1/3 and the 1 over square root of 2 together, getting 1 over 3 square root of 2, inverse tangent of 3x over square root of 2 plus c. Hey, there you go. There's my antideriv. All right. So we've just got one more here to try out. Let's see if you guys can try this one out from beginning to end. And it's going to be a little tricky in a couple parts. If there's any part you get stuck on, what I would recommend is really trying it first, unpausing until you get to that point, and then after I've helped you enough with that point to move on, then try and pause it again and keep going and do as much as you can on your own. So now this one, if you got to this, would be tricky, right? If you're on a test or quiz that's later on in the year after we mix all these techniques together. Again, some people might think, hey, what about the ln rule? Let's try the u prime over u. But if you took the derivative of the bottom would just be 4 e to the 4x. And the problem is the top is e to the 2x. There's no way I could manipulate the top to make it e to the 4x. I could do the 4. That's fine. I could change that, but I couldn't change the e to the 4x. I couldn't make the e to the 2x become a e to the 4x. I couldn't do that. Okay, I can't manipulate variables. So it is going to be this inverse trig thing, and definitely we're going to use our inverse tan formula because there's no square root, okay? So I need to find my a, which remember, the 4 is in the spot where a squared is, so a would just be equal to 2. And I need to find my u, okay? Now this is a little tricky. So the u squared is in the same spot where e to the 4x is, okay? So if I find my u and do the square root of both sides, u is equal to, well, the square root of e to the 4x. Another way I can write, some of you might just know that, but another way I can write square root, right, is write it to the 1/2 power, okay? And then at this point, I could then multiply my exponents and get e to the 2x, which makes sense because if I do e to the 2x times e to the 2x, it becomes e to the 4x, okay? Because in that case, I would add my exponents. So my u is e to the 2x. Beautiful. Now my du is equal to the derivative of u, derivative of e to the 2x is going to be e to the 2x times 2, which is be 2e to the 2x dx. So I look and I'm like, oh, I'm so close. Look at the top. It's e to the 2x. All I'm off is off by a 2. So I can multiply by 2 over 2, okay? And I'll just go down here. And I'm going to go ahead and bring the top 2 inside, leave the bottom 2 outside. So 1/2 integral of 2e to the 2x. Sorry, I wrote that all messy like. Over 4 plus e to the 2x. Okay? Now it's set up perfectly, right? Now I've found I still have the same a and the same u, but now my du is perfectly what it's supposed to be on top right there. It's supposed to be 2e to the 2x. So now I can go ahead and apply my rule. The 1/2 has to go along for the ride, so I put that out front. And then 1 over a, well, a is 2, so I actually have another 1 over 2 there. Then inverse tangent of u over a. Remember, u is e to the 2x, so it becomes e to the 2x over 2 plus c. And of course, I can multiply the half and the half together to get 1/4 inverse tangent of e to the 2x over 2 plus c. So there you have it. Okay. Little practice time here, okay? Have some fun with it. Try and apply what we just learned in this lesson. Please reach out and ask if you have any questions as you're trying to practice some of these. If you're not sure, let me know. And I can, meet up with you or make a video or whatever it is. I want to help you. I want to make sure you feel prepared going into the tests and quizzes for this, all right? Hey, crew, have a great rest of the day, and I will see you next class.